Look up at the night sky, and you'll see countless pinpricks of light stars that have burned for millions, even billions of years. But have you ever wondered where they come from? Hidden within the vast, swirling clouds of gas and dust we call nebulae, something extraordinary happens. These cosmic nurseries, glowing with ethereal light, are where stars are born, where the universe stitches together the very fabric of light and life itself. Today, we're setting out on a journey to uncover the secrets of these uncharted nebulae, the hidden cradles of stellar life. Picture a place where temperatures plunge to near absolute zero, where gravity works its magic over eons, pulling together wisps of gas until they ignite into brilliant new suns. These nebulae aren't just beautiful, they're the engines of creation, sculpting the galaxies we know and love. From the famous Orion Nebula, visible to the naked eye, to remote, undiscovered clouds drifting in the depths of space, each one holds clues to how stars and even planets come into being. But how do these celestial nurseries form? What forces shape them? And what can they teach us about our own cosmic origins? The answers lie in a dance of physics and chemistry so intricate, it's almost poetic. Within these nebulae, atoms collide, molecules bond, and gravity weaves its silent spell, turning chaos into structure. Some nebulae blaze with the light of newborn stars, while others remain shrouded in darkness, their secrets still locked away. Yet every one of them is a testament to the universe's endless creativity. So join us as we venture into these uncharted territories, where science meets wonder, and where every discovery brings us closer to understanding the grand story of the cosmos. This is more than just a journey through space, it's a journey to the very heart of how stars, and perhaps even life itself, begin. To understand how stars are born, we first need to grasp what nebulae really are. Think of them as the universe's raw materials, vast, drifting clouds of gas and dust, some stretching hundreds of light years across. But not all nebulae are the same. Some glow with vibrant hues, lit up by the fierce radiation of nearby stars. These are emission nebulae, where gases like hydrogen are energized until they emit their own light, painting the cosmos in brilliant reds and blues. Then there are reflection nebulae, which don't produce light themselves but act like cosmic mirrors, scattering the light of nearby stars into ethereal blue halos. And lurking in the shadows are dark nebulae, dense, cold clouds so thick with dust they block out the light behind them, appearing as silhouettes against the starry backdrop. What makes these cosmic clouds so special is their role as stellar nurseries. Inside them, gravity slowly pulls together particles of gas and dust, clumping them into ever denser pockets. Over thousands of years, these clumps grow, heating up under their own weight until, like a match struck in the dark, nuclear fusion ignites, and a new star is born. But the process isn't always smooth. Turbulent magnetic fields, shock waves from exploding stars, and even the gentle push of starlight can shape these nurseries, sculpting them into intricate tendrils and pillars. Take the famous pillars of creation in the Eagle Nebula, towering columns where stars are forming right now, hidden within their dusty folds. Yet for all their beauty, nebulae are fleeting. The very stars they birth will one day blow them apart with stellar winds or supernova explosions, scattering their remains to form new generations of stars and planets. It's a cycle as old as the universe itself, one that continues to shape the cosmos around us. And as we peer deeper into these glowing clouds, we're not just uncovering the secrets of star birth. We're tracing the origins of everything, from the atoms in our bodies to the planets that orbit distant suns. the story of nebulae is, in many ways, the story of us. Deep within these swirling clouds of gas and dust, the real magic happens where gravity takes center stage in the universe's grand performance of star birth. Imagine a single speck of dust, no larger than a grain of sand, drifting in the void. Over millions of years, it's joined by countless others, drawn together by an invisible force until the collective weight becomes unbearable. Cloud begins to collapse, fragmenting into dense knots called molecular cores, each one a potential cradle for a new star. Inside these cores, temperatures plummet to near absolute zero, and pressures build to unimaginable levels. Atoms squeeze together so tightly that hydrogen molecules form, and the core starts to glow faintly with the first whispers of heat. This is the birth of a protostar, a stellar embryo still wrapped in its cosmic womb. But the journey from protostar to full-fledged star is anything but gentle. Chaotic magnetic fields twist through the nursery, while fierce radiation from nearby stars strips away layers of gas like a cosmic sandblaster. In some regions, newborn stars themselves become the sculptors, their stellar winds carving vast cavities into the surrounding nebula. The result, breathtaking structures like the pillars of creation, where towers of dust stand defiant against the eroding forces of light. These pillars aren't just static monuments, they're active construction zones, with hidden pockets of gas still collapsing into new stars even as their outer layers are blown away. Yet for every iconic nebula we've captured in stunning detail, there are countless others shrouded in mystery. Far beyond the reach of current telescopes, uncharted nebulae drift through the galactic outskirts, their secrets locked away by distance and darkness. Some may harbor rare, massive stars that burn bright and die young, seeding the cosmos with heavy elements. Others could be nurturing quiet, dim stars like our sun stars capable of hosting planets and perhaps life. With next-generation telescopes like the James Webb Space Telescope peering deeper into infrared wavelengths, we're on the verge of uncovering these hidden nurseries. What will we find? Maybe nebulae where star formation happens at breakneck speeds, or others where it unfolds in slow motion, defying our expectations. Every discovery rewrites the story of how stars, and by extension, galaxies come to be, because these nebulae aren't just factories for stars, they're the architects of the cosmos, shaping the very building blocks of everything we see. The iron in our blood, the silicon in our planet's crust, even the oxygen we breathe, all of it was forged in the hearts of stars born in nebulae like these. So when we gaze at these stellar nurseries, we're not just witnessing the birth of stars, we're glimpsing our own origins, written in the faint glow of distant gas and dust. Molecular clouds are the silent giants of the cosmos, vast, shadowy reservoirs of gas and dust where the ingredients for star birth lie waiting. Unlike the glowing nebulae they often inhabit, these clouds are cold and dark, with temperatures hovering just a few degrees above absolute zero. It's this very chill that makes them perfect stellar nurseries. When gas gets cold enough, atoms slow down and bond together, forming molecules like hydrogen, the primary fuel for new stars. These molecular clouds aren't just scattered randomly, they're structured like cosmic tapestries, with dense knots and filaments weaving through them, each one a potential site for gravity to begin its work. But what triggers these clouds to collapse and ignite star formation? Sometimes it's the shockwave from a nearby supernova, a dying star's final act, sending ripples through space that compress the gas. Other times, it's the gentle push of radiation from young, hot stars nearby, squeezing the cloud until it fractures into smaller clumps. And in some cases, the cloud's own gravity becomes too much to bear, causing it to implode under its own weight. Once a clump reaches a critical density, the real transformation begins. Like a snowball rolling downhill, it gathers more material, growing hotter and denser until the core ignites with nuclear fusion. A star is born. The scale of these clouds is almost incomprehensible. Take the Taurus molecular cloud, for example, a relatively nearby stellar nursery spanning over 400 light-years. Within its depths, dozens of stars are taking shape, some solitary, others in tight-knit clusters. But not all molecular clouds are created equal. Some, like the monster-sized clouds near the center of our galaxy, can spawn thousands of stars at once, creating dazzling clusters that light up the cosmic neighborhood. Others, smaller and quieter, might only produce a handful of stars over millions of years. What's truly fascinating is how these clouds interact with their surroundings. Radiation from newborn stars can erode the very cloud that birthed them, carving out cavities and leaving behind sculpted pillars of dust. Meanwhile, turbulent magnetic fields twist through the gas, shaping how material flows and where new stars can form. It's a dynamic, ever-changing environment, one where chaos and order exist side by side. Scientists are still piecing together all the forces at play, using telescopes that peer into infrared and radio wavelengths to see through the dust and observe the hidden processes within. Every molecular cloud tells a story of how stars come to be, how they shape their surroundings, and how the cycle of birth and death continues to weave the fabric of the universe. And as we uncover more about these cosmic cradles, we're not just learning about distant suns, we're tracing the origins of the elements that make up our world, and perhaps even the conditions that led to life itself. If we could see the universe only in visible light, half its story would remain hidden, especially when it comes to the dusty, gas-filled nurseries where stars are born. That's because thick clouds of cosmic dust act like a curtain, absorbing and scattering the light from objects behind them. But what if we could lift that curtain? Enter infrared astronomy, a game-changing way to observe the universe by detecting heat rather than visible light. Dust that blocks our view in optical wavelengths becomes nearly transparent in infrared, letting us peer straight into the heart of nebulae where stars are taking shape. The James Webb Space Telescope is the crown jewel of this infrared revolution. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb's instruments are tuned to the faint thermal glow of distant objects. This allows it to capture stunning details invisible to other telescopes, like newborn stars still wrapped in their dusty cocoons, or the intricate networks of gas filaments that feed their growth. One of Webb's most breathtaking discoveries, countless protostars in the Orion Nebula, each one a flickering ember in the cosmic dark, their existence completely hidden until now. But infrared astronomy isn't just about seeing through dust, it's also about temperature. Young stars, still gathering material, radiate most of their energy in infrared wavelengths because they're cooler than mature stars. By studying this heat signature, scientists can determine a star's age, mass, and even how fast it's accreting gas. Some of the most surprising finds come from failed stars, known as brown dwarfs, which glow dimly in infrared but never ignite fusion fully. These discoveries blur the line between planets and stars, reshaping our understanding of how celestial objects form. The data pouring in from infrared telescopes is rewriting textbooks. For decades, we assumed star formation followed a predictable sequence, but now we see it's far messier, with stars forming in chaotic bursts, competing for material, and even triggering new waves of birth in nearby gas. In the Carina Nebula, Webb revealed jets of material shooting from young stars at speeds of hundreds of kilometers per second, sculpting the surrounding cloud like interstellar fireworks. And in quieter corners of space, infrared eyes have spotted icy molecules clinging to dust grains, the very building blocks of future planetary systems. Every breakthrough brings us closer to answering fundamental questions. How do stars like our Sun form? What conditions lead to planets and potentially life? With each infrared observation, we're not just filling gaps in our knowledge. We're uncovering a dynamic, hidden universe where the rules of star birth are more complex and wondrous than we ever imagined. And as technology advances, who knows what other secrets these cosmic nurseries will reveal? The dust that once obscured our view is now the very thing guiding us to the heart of creation. The journey of a star begins in chaos, a swirling nebula where gravity slowly sculpts gas and dust into a newborn sun. But that's just the opening act. What happens next is a cosmic saga spanning millions, even billions of years, shaped entirely by a star's mass. Take a massive star 20 times heavier than our Sun. It lives fast and dies young, burning through its fuel in just a few million years. At its core, temperatures soar to millions of degrees, fusing heavier and heavier elements, carbon into neon, neon into oxygen, and eventually iron. But iron is a dead end. Unlike lighter elements, fusion can't extract energy from it. The star's core collapses in seconds, triggering a cataclysmic supernova explosion so bright it outshines entire galaxies. In that blinding flash, elements like gold, uranium, and lead are forged, scattering into space to seed future stars and planets. Smaller stars like our Sun take a gentler path. For 10 billion years, they burn steadily, converting hydrogen into helium in their cores. But even these stars can't escape their fate. As fuel runs low, the Sun will swell into a red giant, engulfing Mercury and Venus, while Earth becomes a scorched cinder. Eventually, it will shed its outer layers in a shimmering display, a planetary nebula. Despite the name, these glowing shells have nothing to do with planets. Instead, they're the star's final breath, expanding into space like cosmic smoke rings. At the center, the Sun's core will remain as a white dwarf, a dense, Earth-sized ember that cools over trillions of years. Yet the most mysterious stars are those in between. 8 times the Sun's mass, they face an explosive demise or collapse into neutron stars, objects so dense a teaspoon of their material weighs 1 billion tons. Some neutron stars spin rapidly, beaming radiation like cosmic lighthouses. We call these pulsars. Others, locked in binary systems, siphon material from a companion star until they detonate in runaway thermonuclear explosions. And in the rarest cases, stars so massive they leave behind black holes, warping space-time itself. This cycle of birth and death isn't just poetic, it's essential. Supernova blast heavy elements into nebulae, enriching them for the next generation of stars and planets. Without these explosions, Earth wouldn't have the iron in its core or the oxygen in our air. Even the atoms in your body were forged in distant stellar furnaces, scattered across space before finding their way here. What's next? Telescopes like the Vera Rubin Observatory will scan the skies for supernova in real time, while gravitational wave detectors listen for the ripples from colliding neutron stars. Each discovery peels back another layer of this cosmic story, revealing how stars shape and reshape the universe. From the faintest white dwarf to the most brilliant supernova, every star's fate is written in the laws of physics, yet each one leaves behind a legacy that echoes across the cosmos. Beyond the familiar glow of Orion and Carina lies a universe of uncharted nebulae, vast, mysterious regions where our understanding of star formation is still being written. These cosmic frontiers are like blank pages in the galaxy's storybook, each one holding the potential to rewrite what we know. While iconic nebulae have taught us the basics of stellar birth, it's the unexplored clouds that often reveal the exceptions, the oddities, the rules we didn't know existed. Take the recently discovered dark galaxies, nebulae so diffuse and star-poor they're nearly invisible. Yet they hint at a slower, quieter mode of star formation we've barely begun to understand. Then there are the extreme environments, like nebulae nestled near supermassive black holes, where gravity and radiation warp star formation into something entirely alien. In these chaotic zones, stars might form at breakneck speeds or in bizarre configurations, defying the tidy models we've built from common nurseries. And let's not forget the isolated nebulae, lonely clouds drifting far from the galaxy's bustling spiral arms. Without the trigger of nearby supernova or stellar winds, how do stars ignite here? The answers could reveal entirely new pathways to stellar birth. Technology is our compass in this uncharted territory. The James Webb Space Telescope's infrared eyes pierce through dust veils, while radio telescopes like ALMA detect the faint whispers of molecules like methanol and formaldehyde traces of chemistry we once thought impossible in space. Already, these tools have spotted nebulae rich in complex organic compounds, the kind that could seed prebiotic chemistry on planets. Could some of these hidden clouds harbor the ingredients for life? It's not just speculation. In 2020, astronomers found a nebula with ethanol, yes, the same alcohol found in drinks floating in space, alongside sugars and other building blocks of biology. The hunt for these cosmic unknowns isn't just about filling gaps on a map. It's about confronting the surprises that force us to rethink, like the rogue nebulae speeding through intergalactic space, untethered to any galaxy. How did they get there? What stars might form in such isolation? Every discovery peels back another layer, showing us that the universe is far more inventive than our textbooks suggest. And as next-generation telescopes come online, one thing is certain: the golden age of nebula exploration has only just begun. The darkest corners of the galaxy aren't empty, they're hiding stories we've yet to imagine. Dark nebulae are the cosmic equivalent of a stage draped in black velvet silhouettes so dense they swallow the light behind them, leaving only a void against the glittering backdrop of stars. But these aren't empty spaces. They're some of the most fertile grounds for star birth in the universe, where dust and gas pile up so thickly that gravity can work its magic undisturbed. Picture the Horsehead Nebula, its iconic shape carved by stellar winds, standing like a sentinel in Orion. Yet for every famous dark nebula, there are thousands of others, unnamed and uncharted, their secrets locked away behind curtains of cosmic dust. What makes these shadowy regions so special? It's their density. While emission nebulae glow with the energy of newborn stars, dark nebulae are cold and quiet, their interiors shielded from the chaos outside. That stillness allows molecules to clump together more easily, forming the seeds of future stars. Inside these clouds, temperatures drop to just a few degrees above absolute zero, and pressures mount until hydrogen atoms pair up, creating the fuel for nuclear fusion. Some dark nebulae, like Barnard 68, are so opaque they block out all visible light, acting like cosmic cocoons where stars can form in near-total isolation. But darkness doesn't mean inactivity. Radio telescopes have revealed a hidden world within these clouds, complex molecules like carbon monoxide and even amino acids clinging to dust grains. These chemical factories might hold the key to understanding how the building blocks of life spread through the galaxy. And then there's the turbulence. Magnetic fields twist through dark nebulae like invisible threads, shaping how gas collapses and where stars ignite. In some cases, the sheer weight of a nebula's outer layers triggers a chain reaction, fragmenting the cloud into smaller cores, each one a potential stellar nursery. The Horsehead Nebula might be the poster child, but lesser-known dark nebulae are just as fascinating. Take the Coalsack Nebula, a vast shadow near the Southern Cross, or the Snake Nebula, a sinuous ribbon of dust slithering across the Milky Way. These structures challenge our assumptions. Some appear to be starless, with no signs of active formation yet. Others, like the Pipe Nebula, are dotted with newborn stars peeking through gaps in the dust like fireflies in fog. Unlocking their mysteries isn't easy. Visible light telescopes see only the outlines, but infrared and radio observations pierce the veil, revealing protostars still wrapped in their dusty blankets. Some dark nebulae might be the birthplaces of rare, massive stars, while others could nurture quiet, low-mass stars like our Sun. And then there's the tantalizing possibility of failed stars, brown dwarfs, too small to ignite fusion but lurking in the dark, rewriting the rules of what constitutes a star. Every dark nebula is a time capsule, preserving the raw materials of star formation in their most pristine state. They remind us that the universe's most creative work often happens in the shadows, away from the spotlight. And as we learn to see through their darkness, we're not just discovering new stars, we're uncovering the hidden blueprints of cosmic evolution, one shadowy silhouette at a time. A supernova isn't just an ending, it's a spectacular rebirth. When a massive star detonates, it unleashes energy equivalent to 1 billion suns, shredding its outer layers into a frenzied storm of gas and debris. What remains is a supernova remnant, a cosmic crime scene where forensic astronomy pieces together the star's final moments. Take the Crab Nebula, a tangled web of filaments glowing in eerie blues and oranges. At its heart lies a pulsar, a spinning neutron star born from the original star's collapsed core, beaming radiation like a lighthouse. But the real magic happens in the expanding shockwave, where the blast rams into surrounding gas, compressing it into glowing tendrils and triggering new waves of star formation. These remnants are more than just beautiful wreckage, they're galactic recyclers. As the shockwave races outward at thousands of kilometers per second, it scatters heavy elements forged in the star's death throes: iron, gold, even uranium. These atoms mix with nearby nebulae, enriching them with the raw materials for rocky planets and life. Without supernova, Earth's core wouldn't have its iron, nor would our oceans hold oxygen. Every ingredient in your body, from the calcium in your bones to the zinc in your enzymes, was once blasted into space by such an explosion. Yet not all remnants are created equal. Some, like the delicate Veil Nebula, resemble ghostly lace, their filaments so thin they're nearly transparent. Others, like Cassiopeia A, glow in X-rays as they heat surrounding gas to millions of degrees. And then there's the mysterious supernova imposter, remnant structures like Eta Carinae's homunculus nebula, where stars didn't fully explode but instead ejected colossal shells of material in violent outbursts. These oddballs challenge our definitions, showing that stellar death comes in many flavors. What's astonishing is how long these remnants linger. While the initial explosion lasts mere weeks, the aftermath can unfold for millennia. The Cygnus Loop, for instance, has been expanding for 20,000 years, its shock front still plowing through interstellar space. Along the way, it rams into molecular clouds, squeezing them until new stars ignite. It's a cosmic domino effect. One star's death becomes the spark for another's birth. Modern telescopes reveal even stranger details. Infrared observations show dust grains condensing in the cooling ejector, while radio maps uncover molecules like silicon monoxide forming in the chaos. Some remnants, like W44, even harbor cosmic rays, particles accelerated to near light speed by the shock waves, zipping through the galaxy. These discoveries paint a picture of remnants as dynamic laboratories, where physics operates at extremes we can't replicate on Earth. The legacy of a supernova isn't just destruction, it's transformation. By studying these remnants, we're tracing how the universe redistributes its building blocks, turning stellar graves into nurseries for the next generation. And somewhere out there, a future nebula is waiting, its chemistry enriched by an explosion that hasn't even happened yet. When it does, the cycle will begin anew. Deep within the swirling chaos of a stellar nursery, where gravity pulls gas and dust into the beginnings of a new star, something extraordinary happens, a cosmic tantrum of sorts. As the young star gathers material from its surroundings, it doesn't just grow quietly. Instead, it launches narrow, high-speed jets of gas, shooting outward like twin fire hoses at nearly 500,000 miles per hour. These protostellar jets are some of the most dramatic signatures of star birth, etching delicate, glowing trails across the nebula that can stretch for light years. What's fascinating is how these jets form. As the protostar spins, it drags magnetic fields along with it, twisting them into powerful spirals. Some of the infalling gas gets funneled along these magnetic lines, redirected toward the star's poles, and then blasted into space. The result, a pair of searingly hot, ionized beams that punch through the surrounding cloud, often colliding with slower-moving gas and creating shockwaves that glow in vivid hues. Hubble's iconic images of the Orion Nebula reveal these jets in stunning detail, some appearing as delicate, knotted threads, others as broad, fan-shaped outflows, each one a snapshot of a star's violent adolescence. But these jets aren't just celestial fireworks, they serve a critical purpose. By ejecting excess energy and angular momentum, they allow the young star to keep growing without spinning itself apart. Without these outbursts, many stars might never stabilize enough to ignite sustained fusion, and the jets do more than just regulate the star, they sculpt their surroundings. In the HH34 system, for example, a jet has carved a bipolar cavity, clearing out material and even triggering secondary star formation in distant pockets of the nebula. It's a ripple effect where one star's birth influences the next. Some of the most extreme jets come from massive protostars, which can produce outflows so powerful they disrupt entire swaths of their birth cloud. In rare cases, like the Object Era's 20,126 plus 41014, jets have been observed twisting into corkscrew shapes, likely due to the gravitational pull of an unseen companion star or planet. These structures are like cosmic fingerprints, revealing the hidden dynamics of systems still in their infancy. Yet for all their fury, protostellar jets are fleeting. As the star matures and its accretion disk dwindles, the jets fade, leaving behind only the ghostly traces of their once fiery paths. But while they last, they're a dazzling reminder of the universe's creativity, a testament to how even the birth of something as seemingly serene as a star is a storm of forces, magnetic fields, and sheer cosmic spectacle. And with every new observation, we're learning just how much these jets shape not only their stars but the very nurseries that birthed them. The pillars of creation stand like ancient sentinels in the Eagle Nebula, their towering columns of gas and dust immortalized by Hubble's iconic 1995 image. But these structures are more than just a breathtaking cosmic postcard. They're a living laboratory where stars are born and destroyed in real time. Recent observations suggest these pillars might already be gone, vaporized by a shockwave from a nearby supernova that occurred 6,000 years ago. Because light takes time to travel, we're still seeing their ghostly silhouette, a celestial echo of what once was. Yet even in their apparent demise, they teach us something profound about the life cycle of nebulae. Zoom in with modern telescopes like James Webb, and the pillars reveal secrets Hubble couldn't see. Nestled within their dusty folds are newborn stars, some still swaddled in cocoons of gas, others blasting out jets that carve delicate cavities into the surrounding material. Infrared light pierces through the obscuring dust, exposing intricate networks of filaments and knots where gravity is actively sculpting the next generation of stars. Some of these protostars are barely larger than Jupiter, while others, hidden deeper within, may one day outshine our Sun. The pillars aren't just passive sculptures, they're dynamic factories, with stellar winds and radiation constantly reshaping them. Physics plays out on a grand scale here. The pillars' famous fingers are being eroded by ultraviolet light from nearby massive stars, a process called photoevaporation. Gas heats up and boils away, leaving behind denser clumps that shield the material behind them, creating the illusion of shadowy fingertips. But this erosion isn't just destruction, it's also triggering new star formation. As the outer layers are stripped away, compressed gas inside collapses under its own weight, igniting fresh stellar nurseries in the pillars' hearts. It's a paradox. The very forces tearing the pillars apart are also sowing the seeds of their rebirth. What's next for this cosmic landmark? Simulations suggest the pillars may only last another few 100,000 years, a blink in cosmic time. When they're gone, the stars they nurtured will disperse, their radiation and winds blowing away the remaining gas. But the cycle won't end there. The heavy elements forged in those stars will eventually mix with interstellar space, enriching future nebulae with the building blocks for planets and perhaps life. The pillars of creation remind us that beauty in the universe is fleeting, but transformation is eternal. Every collapse is a prelude to creation, and every ending is just a different kind of beginning. For now, these pillars remain one of the universe's most powerful metaphors. They show us the delicate balance between chaos and order, destruction and renewal. And as telescopes grow sharper, who knows what other lessons they'll yield? Whether as ruins or active nurseries, their legacy is secure, a testament to the universe's relentless creativity, written in gas, dust, and light. Bok globules are the universe's way of proving that big things often come in small packages. These dense, dark knots of gas and dust drift through nebulae like shadowy islands, each one a potential cradle for a single star or a tiny stellar system. Named after astronomer Bok, who first studied them in detail, these compact clouds are the cosmic equivalent of a cocoon, isolated, serene, and shielded from the chaos of their bustling surroundings. While massive nebulae like Orion dominate the spotlight, it's these unassuming globules that offer scientists a clearer, simpler window into how stars are born. What makes them so special? Unlike sprawling molecular clouds, where competing forces of gravity, radiation, and turbulence create a chaotic star-forming frenzy, Bok globules are relatively quiet and self-contained. Picture a snowball rolling through space, gathering more material as it goes, until the core becomes so dense and hot that nuclear fusion ignites. That's the essence of star formation in these tiny nurseries, a process stripped down to its fundamentals, free from the interference of nearby stars or magnetic storms. Some globules are so small they could fit within our solar system, yet they pack enough material to forge a star or two. But not all globules succeed in their stellar ambitions. Some may give rise to brown dwarfs, objects too massive to be planets but too small to sustain full-fledged fusion. These cosmic, almost stars, glow faintly with residual heat, a reminder that even in the universe, not every beginning leads to a brilliant destiny. Studying these failed stars is like finding a missing link in the story of stellar evolution, helping us understand why some clouds ignite into suns while others fizzle into dim, Jupiter-sized embers. The real magic lies in their transparency. Because Bok globules are small and isolated, astronomers can peer into them with remarkable clarity, tracing the subtle motions of gas and dust as they spiral inward. Radio telescopes have detected molecules like carbon monoxide inside these globules, revealing the chemical groundwork being laid for future planetary systems. Some even show hints of icy coatings on dust grains, water, methane, and ammonia frozen solid in the deep cold of space. These ices could one day become the building blocks of comets or oceans on distant worlds. One of the most famous examples is Barnard 68, a dark, nearly spherical globule just 500 light-years away. Invisible light, it's an inky blot against the starry backdrop, but infrared observations pierce through, showing a core on the verge of collapse. Will it form a star, a brown dwarf, or simply dissipate over time? Each possibility teaches us something new about the delicate balance required for star birth. The study of Bok globules is rewriting the rules of how stars form, especially at the lower end of the size spectrum. They challenge the idea that star formation is always a dramatic, large-scale event, proving instead that it can happen in quiet corners, one modest cloud at a time. And as telescopes grow more powerful, these tiny cosmic incubators may hold the key to answering one of astronomy's biggest questions. What's the smallest object that can truly be called a star? The answer could redefine our understanding of the universe's diversity and our place within it. Magnetic fields are the silent architects of stellar nurseries, weaving invisible threads through the chaos of nebulae to shape how stars are born. While gravity pulls gas and dust together, these magnetic forces act like cosmic traffic controllers, directing the flow of material with precision. Picture a nebula not as a formless cloud, but as a vast network of magnetic highways. Some regions funnel gas into dense streams, while others create barriers that slow collapse, stretching the process over millennia. Without these fields, star formation would be a far messier, more explosive affair, with gas collapsing haphazardly into stars of all sizes. Instead, magnetism brings order to the chaos, sculpting the nurseries where solar systems take shape. One of the most striking examples lies in protoplanetary disks, the swirling rings of debris around young stars where planets eventually form. Magnetic fields play a crucial role here, twisting the disk's inner layers into funnel-like shapes that launch jets of material into space, like those seen in the Orion Nebula. These jets aren't just spectacular to observe, they are evidence of an intricate balance. As gas spirals toward the newborn star, magnetic forces channel some of it away, preventing the star from spinning too fast and tearing itself apart. It's a celestial feedback loop where magnetism regulates growth, ensuring stars form at just the right pace. But magnetic fields don't just guide, they also resist. In some dense regions of nebulae, particularly where gas is cold and ionized, these fields can become strong enough to counteract gravity, putting star formation on hold. Observations of the Taurus molecular cloud reveal pockets where magnetic pressure stalls collapse, creating eerie, frozen-in-time zones where gas hovers in equilibrium. Only when turbulence or external shockwaves disrupt this balance does gravity finally win, triggering a burst of new stars. This delicate tug of war explains why some nebulae seem to form stars in fits and starts rather than all at once. Recent breakthroughs in polarimetry, a technique that measures the alignment of light waves, have let scientists map these invisible fields like never before. The results are astonishing. In the Crab Nebula, magnetic fields form an intricate lattice like a cosmic spiderweb, while in the pillars of creation, they twist along the towering columns, reinforcing their structure against erosion. Even more surprising are the hourglass fields found around protostars, where magnetic lines pinch tightly near the star's poles, shaping the jets that blast outward. Each discovery reveals how deeply magnetism is woven into the fabric of star birth. Yet mysteries remain. In massive nebulae near galactic centers, magnetic fields appear to amplify chaos rather than tame it, driving gas into violent whirlpools that birth super-sized stars. Meanwhile, in low-mass clouds, fields seem quieter, acting more like gentle guides. Why the difference? The answer may lie in the nebulae's history, whether they were seeded by ancient supernova or formed in isolation. What's clear is that no two nurseries are alike, and magnetism ensures each one tells its own unique story. As telescopes grow sharper, we're on the verge of decoding these cosmic blueprints in full. From the delicate dance of dust grains aligning with magnetic lines to the explosive reconnection events that release stored energy, every clue brings us closer to understanding how these invisible forces shape not just stars, but the planets and perhaps life that orbit them. The universe, it seems, writes its grandest tales not just in light and gravity, but in the quiet, persistent pull of magnetism. Every star that dies leaves behind a gift, a legacy written in atoms scattered across the cosmos. When a star reaches the end of its life, whether in a quiet whisper or a supernova's roar, it doesn't just vanish. It exhales its essence into space, enriching the interstellar medium with elements crafted in its core. Carbon, oxygen, silicon, even gold, these are the ashes of stellar furnaces, and they become the building blocks for everything that follows. Nebulae, those sprawling clouds of gas and dust, are the cosmic workshops where this recycled material is gathered, mixed, and forged anew. Take the Crab Nebula, for instance. Within its tangled filaments, spectroscopy reveals the fingerprints of sulfur, argon, and neon elements forged in the heart of the star that exploded 1,000 years ago. These atoms don't linger idly. Drifting through space, they collide with other remnants, merging into molecular clouds that will one day collapse into new stars. It's a process as old as the universe itself. Our own solar system is a product of this recycling. The iron in Earth's core, the oxygen we breathe, even the calcium in our bones, all of it was once part of a star that died before the sun was born. But this cycle isn't just about ingredients. It's a driver of galactic evolution. Early in the universe's history, stars formed from pristine hydrogen and helium, with no heavier elements to seed planets. As generations of stars lived and died, they peppered the cosmos with metals, astronomers' term for any element heavier than helium. This gradual enrichment changed the rules of star formation. Metal-rich clouds cool more efficiently, allowing gas to condense into smaller, more numerous stars. Some of these stars, in turn, become the anchors for rocky planets. Without those recycled elements, galaxies would look radically different, brighter, bluer, and devoid of the complex chemistry that makes life possible. The Orion Nebula offers a front-row seat to this process in action. Its vibrant hues aren't just for show. The red glow comes from hydrogen, while the blue regions reflect light off dust grains laced with silicon and carbon. Nestled within are protoplanetary disks, infant solar systems where those same elements are clumping together into planets. Some of those worlds might one day harbor oceans, mountains, or even life, all made possible by the death throes of ancient stars. Yet the story doesn't end there. Supernovae aren't the only contributors. Smaller stars, like our Sun, shed their outer layers more gently, creating planetary nebulae that bloom like cosmic flowers. These expanding shells are rich in nitrogen and carbon, elements crucial for organic chemistry. Even the slow decay of white dwarfs adds to the mix as their atmospheres leak heavy elements into space over billions of years. Every source leaves its mark, creating a galactic ecosystem where nothing is wasted. What's astonishing is the scale. A single supernova can seed an entire nebula with enough iron to build thousands of Earths. Over billions of years, galaxies churn through this material, each generation of stars building on the last. The Milky Way, for example, has recycled its gas multiple times over, with our Sun belonging to the third or fourth generation of stars to form from this enriched reservoir. This grand cycle raises profound questions. Could some nebulae be richer in certain elements, creating stars and planets with unique compositions? Are there regions where the mix is just right to spark life more readily? As we peer deeper into nebulae with tools like the James Webb Space Telescope, we're not just studying star birth, we're tracing the genealogy of matter itself from the first stars to the planets that orbit their descendants. And in that story, we find our own origins written in stardust. The Great Orion Nebula is more than just a dazzling spectacle in the night sky. It's a bustling cosmic workshop where the secrets of star birth unfold in real time. Located just 1,500 light-years away, this stellar nursery is so close that even amateur telescopes can glimpse its swirling gases and newborn stars. But what makes Orion truly special is its sheer intensity. Unlike quieter nebulae where star formation unfolds slowly, Orion is a maelstrom of activity. Massive young stars, some dozens of times heavier than our Sun, blast the surrounding gas with ultraviolet radiation, sculpting vast cavities and triggering chain reactions of new star formation. The result, a celestial fireworks show where gravity, radiation, and magnetism collide in a dazzling display. At the heart of the nebula lies the trapezium cluster, a tight-knit group of hot, brilliant stars that act like cosmic blowtorches. Their fierce energy ionizes the surrounding hydrogen gas, making it glow in vibrant reds and pinks, a signature feature of emission nebulae. But look closer and the real magic emerges. Nestled within the shadows of these giants are protoplanetary disks, flattened rings of gas and dust where planets are taking shape. The Hubble Space Telescope has spotted hundreds of these disks, some as small as our solar system, others stretching wider than Pluto's orbit. Each one is a potential birthplace for worlds with chemistry as diverse as the stars they orbit. Yet Orion doesn't just follow the rules, it breaks them. Astronomers have discovered rogue planets drifting untethered through the nebula, worlds flung from their orbits by gravitational tugs, or perhaps born in isolation from collapsing gas clumps. Then there are the brown dwarfs, objects too massive to be planets but too small to ignite fusion. These cosmic misfits glow faintly in infrared, challenging our definitions of what constitutes a star. Some even host their own miniature disks, hinting at the possibility of moons forming around these failed stars. The surprises don't stop there. Recent observations from the James Webb Space Telescope reveal intricate tendrils of carbon-rich molecules weaving through the nebula compounds that could one day become the building blocks of life. In one stunning discovery, Webb detected water vapor in a protoplanetary disk, suggesting that the ingredients for oceans might be common in such nurseries. Meanwhile, radio telescopes have picked up the faint whispers of complex organic molecules, including methanol and formaldehyde, further blurring the line between chemistry and biology. What's next for Orion? With every new observation, the nebula reveals another layer of complexity. Some theories suggest that shockwaves from dying stars nearby could be compressing the gas, accelerating star formation in unexpected ways. Others propose that hidden black holes or neutron stars might be lurking in the chaos, their gravity subtly shaping the nebula's structure. One thing is certain, Orion is far from done teaching us. As telescopes grow more powerful, this cosmic laboratory will continue to challenge our assumptions, offering front-row seats to the universe's most creative processes. From the tiniest dust grains to the most massive stars, every discovery here rewrites the story of how solar systems, and perhaps life itself, come to be. Infant stars are anything but peaceful. These cosmic toddlers throw tantrums that put even the most energetic supernova to shame. Picture a newborn star, barely a few 100,000 years old, already blasting jets of superheated gas at nearly 500,000 miles per hour. These outbursts aren't just random fits of cosmic rage, they're essential to the star's survival. As gravity pulls more material onto the young star, its rotation speeds up, threatening to tear it apart. But magnetic fields channel some of that energy into twin jets, shooting outward from the poles like safety valves, stabilizing the star before it spins itself into oblivion. The chaos doesn't stop there. Protoplanetary disks, those swirling rings of gas and dust surrounding these infant stars, are battlegrounds where competing forces shape the future of entire solar systems. Gravity pulls material inward while heat and radiation push it outward. Magnetic fields twist the disk into intricate spirals, creating lanes where dust grains clump together, forming the first seeds of planets. Some regions grow so dense they trigger gravitational instabilities, collapsing into Jupiter-sized worlds in just a few thousand years. Others remain turbulent for millions of years, their dust grains colliding, shattering, and reforming in an endless dance. But the real drama unfolds when these young stars flare. Unlike our sun's relatively mild solar flares, infant stars unleash eruptions thousands of times more powerful. In the Orion Nebula, astronomers have observed flares so intense they briefly outshine the star itself, bombarding nearby disks with enough X-rays to vaporize ice and alter chemistry. These outbursts may explain why some planetary systems end up with dry, rocky worlds close to their stars, while others retain icy giants farther out. Perhaps the most astonishing discovery is how quickly planets can form in these chaotic environments. In the disk around the star HL Tauri, radio telescopes have spotted concentric gaps, clear signs of infant planets carving paths through the dust. Some of these worlds may have formed in just 1 million years, a blink in cosmic time. Yet not all disks are so lucky. In systems like Beta Pictoris, massive collisions between protoplanets send shockwaves through the disk, scattering debris into vast, glowing rings. What does this mean for our own solar system's history? The Sun was once one of these tempestuous toddlers, its disk a swirling maelstrom where Earth's building blocks jostled for survival. The same flares that sterilize young systems may have also forged complex molecules in ours. The same magnetic storms that shape alien worlds likely guided the formation of Jupiter and Saturn. By studying these infant stars, we're glimpsing our own origins not as a serene, orderly process, but as a cosmic free-for-all where chance and physics conspired to build the only home we've ever known. Massive stars are the universe's paradoxes, celestial giants that shouldn't exist, yet shine brighter than entire galaxies, while a star like our Sun forms steadily, gathering mass over millions of years. A massive star faces a cosmic catch-22. The moment its core ignites, the resulting radiation and stellar winds should blast away the surrounding gas, cutting off its own fuel supply. So how do these titans, some weighing in at over 100 solar masses, defy physics to reach such staggering sizes? The answer lies in a high-stakes race against time, where gravity and radiation wage a battle that reshapes entire nebulae. One leading theory suggests these stars grow through a process called competitive accretion. Picture a crowded stellar nursery where multiple protostars vie for the same pool of gas. The largest protostar, with its stronger gravity, hoards material faster than its smaller siblings, creating a feedback loop. The more it eats, the more it can eat. In dense regions like the Tarantula Nebula, where gas is plentiful and turbulence runs high, this winner-takes-all scenario might allow a few stars to balloon to extraordinary sizes. But there's a twist. Mergers could also play a role. Recent simulations show that young massive stars might collide and merge in the chaotic environment of a nebula's core, their combined mass catapulting them into the heavyweight league. Yet even these explanations don't fully account for their survival. A star 20 times the Sun's mass emits ultraviolet radiation so intense it can ionize gas clouds light years away, carving out vast cavities in its birthplace. This radiation pressure should, in theory, halt further growth, but observations of nebulae like NGC 6357 reveal a clue. Some massive stars are born in dense, dusty cocoons that shield them from their own destructive power. These cocoons act like cosmic incubators, allowing the star to keep feeding until it's too late for radiation to stop it. The impact of these giants is as profound as their origins. Their fierce ultraviolet light ionizes hydrogen in nebulae, creating glowing H2 regions that become beacons across the galaxy. Their short, explosive lives end in supernovae that scatter heavy elements like oxygen and iron, enriching the cosmos for future generations of stars and planets. And when they die, their shockwaves can compress nearby gas, triggering waves of new star formation, a ripple effect that shapes galactic evolution for eons. The mystery isn't just academic. Understanding massive stars means unraveling the history of our own galaxy. Many of the elements in our bodies were forged in their cores or their explosive deaths. Their light illuminates the darkest corners of nebulae, revealing secrets about how solar systems form. And with telescopes like James Webb peering into stellar nurseries with unprecedented clarity, we're on the verge of cracking the code. Every massive star is a cosmic rebel, breaking the rules to light up the universe, and in their defiance, they hold the keys to some of astronomy's deepest questions. Deep within the swirling chaos of a stellar nursery, something extraordinary is happening. Molecules are coming together in ways that blur the line between chemistry and biology. These nebulae aren't just cosmic sculptures of gas and dust. They're vast chemical laboratories where simple atoms collide and bond, forming compounds that could one day become the foundation of life. Take water, for example. Frozen onto dust grains in the frigid depths of a molecular cloud, water molecules accumulate layer by layer, creating tiny icy mantles that will eventually vaporize when a new star ignites nearby. But water's just the beginning. Telescopes have detected formaldehyde, methanol, even glycolaldehyde, a simple sugar, floating in these clouds, each discovery adding another piece to the puzzle of how complex chemistry emerges in the void of space. The process starts with the most abundant element in the universe, hydrogen. In the cold, dense cores of nebulae, hydrogen atoms pair up to form molecules, while carbon, oxygen, and nitrogen latch onto dust grains, creating microscopic meeting places for chemical reactions. Ultraviolet light from nearby stars or cosmic rays provide the energy to kickstart these interactions, breaking and forging bonds in a dance that's been ongoing for billions of years. Some of the most surprising finds come from radio telescopes, which pick up the faint signals of molecules like methyl cyanide or vinyl alcohol compounds that on Earth are associated with industrial processes or even biology. But how do these molecules survive the violent environment of a stellar nursery? The answer lies in the shadows. Dense clumps of gas act like cosmic bunkers, shielding delicate molecules from destructive radiation. Deeper still, ices coating dust grains serve as protective matrices, allowing complex chemistry to unfold in relative safety. When a protostar finally heats its surroundings, these ices sublimate, releasing their molecular cargo into the surrounding disk where planets will form. It's a delivery system millions of years in the making, ensuring that the building blocks of life are present from the very beginning of a solar system. Perhaps the most tantalizing discoveries are the amino acids found in meteorites, which likely formed in nebulae before being incorporated into asteroids. If these organic molecules can arise naturally in space, it raises a profound question: how far can cosmic chemistry go? Could nebulae be seeding the galaxy with the precursors to proteins, DNA, or even more complex structures? While we haven't yet found evidence of life's direct origins in space, each new detection, from the Eagle Nebula's ethanol to the Taurus cloud's carbon chains, hints at a universe that's pre-wired for chemistry far more intricate than we once imagined. Astrochemists are now mapping these molecular nurseries in unprecedented detail, using tools like the Atacama Large Millimeter Array to trace the distribution of organic compounds across star-forming regions. What they're finding is a cosmic recipe book where temperature, density, and radiation levels determine which molecules form and where. Some nebulae are rich in hydrocarbons, others in nitrogen-bearing compounds, each blend influencing the kind of chemistry that might emerge on future planets. And with next-generation telescopes set to probe even deeper, we may soon uncover whether the universe has a preference for certain molecular pathways, ones that could lead, inevitably, to life. This isn't just about distant clouds of gas, it's about our own origins. The same molecules drifting through Orion or the Perseus Arm once swirled in the nebula that birthed our sun. The water in your glass, the carbon in your cells, even the complex organics that sparked life on Earth, all of them began their journey in the chemical cauldron of a stellar nursery. Every time we peer into these cosmic clouds, we're not just studying star formation, we're reading the ingredients list of existence itself. The Lagoon Nebula blazes like a celestial watercolor, its pink and crimson gases swirling around inky filaments of dust, a stellar nursery where beauty and violence intertwine. Stretching 55 light-years across and lying 5,000 light-years away, this nebula is close enough for telescopes to reveal its secrets in stunning detail. At its heart lies Herschel 36, a young star so massive and luminous that its ultraviolet radiation ionizes the surrounding hydrogen, making the entire cloud glow with an otherworldly radiance. But this brilliance comes at a cost. The same energy that lights up the lagoon also tears it apart, carving cavernous bubbles and towering pillars where gas is either boiling away or being compressed into new stars. It's a cosmic paradox. The very stars that illuminate the nursery are also the ones shaping its fate. Zoom in, and the nebula's intricate structure unfolds. Dark, snaking lanes of dust divide the glowing gas-like channels in a lagoon, hence its name, while delicate tendrils stretch outward, sculpted by stellar winds. Nestled within these shadows are Bok Globules, dense pockets of gas resisting the radiation onslaught, each one a potential cradle for future stars. Meanwhile, the lagoon's most famous feature, the Hourglass Nebula, dazzles with its pinched waste of glowing material, a shape carved by the fierce outflow from a newborn star. This tiny region alone is a microcosm of the entire nebula's story, where creation and destruction happen side by side. What makes the lagoon such a perfect laboratory is its sheer diversity of stellar activity. Here, astronomers have spotted everything from massive O-type stars, burning hot and dying young, to faint T-Tauri stars, stellar infants still gathering material from their surroundings. Some of these young stars are surrounded by protoplanetary disks, while others blast out jets that stretch light years into space. The lagoon doesn't just host one generation of stars, it's a multi-generational hub where each wave of star birth influences the next. When massive stars explode as supernova, their shockwaves trigger new rounds of star formation, while their stellar winds clear away debris, exposing younger siblings to the harsh interstellar environment. Yet the lagoon's true lesson lies in balance. For every region where radiation obliterates gas clouds, there's another where that same pressure squeezes material just enough to ignite new stars. In one stunning example, the nebula's stellar kindergarten contains dozens of newborn stars clustered so tightly they could fit within our solar system. How did they form so close together without tearing each other apart? The answer may lie in the delicate interplay between gravity and turbulence, a dance where chaos and order find an uneasy truce. As telescopes like James Webb peer deeper into the lagoon's dust-shrouded corners, they're uncovering surprises. Recent infrared images reveal previously hidden protostars, some so young they're still swaddled in gas, while others show signs of spiral arms in their disks, hints of planets forming in real time. Even more intriguing are the complex organic molecules detected in the nebula's colder regions, the same compounds that might one day seed life on distant worlds. The lagoon isn't just a snapshot of star birth, it's a dynamic ecosystem evolving with each passing millennium. What does this mean for our understanding of the cosmos? The lagoon teaches us that star formation isn't a solo act, it's a symphony, where massive stars conduct the movements of their smaller siblings. Their radiation, winds, and eventual deaths write the rules of the nursery, determining which stars thrive and which regions fall silent. And as we study this vibrant nebula, we're not just observing a distant cloud of gas. We're witnessing the universal processes that shaped our own sun and planets, a reminder that the story of the lagoon is, in some small way, the story of us all. The next decade of nebula exploration promises to rewrite astronomy textbooks, thanks to a new generation of telescopes designed to see the unseen. The James Webb Space Telescope has already dazzled us with its infrared eyes, revealing protostars hidden within the pillars of creation and organic molecules swirling in distant disks. But this is just the opening act. Soon, ground-based behemoths like the extremely large telescope will join the hunt, with mirrors so vast they could collect enough light to spot a car's headlights on the moon. These instruments won't just take prettier pictures, they'll decode the physics of star birth with forensic precision, measuring the subtle tug of magnetic fields on gas streams or clocking the rotation speeds of infant planetary systems. One revolutionary target, the earliest moments of star formation, when a molecular cloud first begins to fragment. Current telescopes glimpse this process like a blurry snapshot, but next-gen instruments will track it in real time, watching as gravity sculpts wispy gas into dense cores. The extremely large telescope's adaptive optics will cancel out Earth's atmospheric distortion, revealing details as small as a few astronomical units. It's close enough to spot gaps in protoplanetary disks where fledgling worlds are carving their orbits. Meanwhile, space-based observatories like the Nancy Grace Roman Telescope will map entire nebulae in 3D, tracing how shockwaves from dying stars propagate through the gas, triggering chain reactions of new star birth. But the holy grail lies in chemistry. The James Webb Space Telescope has already spotted water and carbon dioxide in planet-forming disks, but future spectrographs will hunt for far more complex molecules, amino acids, sugars, even potential biosignatures like methane-oxygen imbalances. Imagine identifying a disk where the chemical precursors for life are abundant, or catching the moment when icy pebbles deliver water to a young, rocky world. Radio telescopes like the Next Generation Very Large Array will complement these findings by mapping the distribution of organic molecules across entire nebulae, showing how these ingredients spread from stellar nurseries to planetary systems. Perhaps the most tantalizing possibilities involve magnetic fields, the invisible architects of star formation. New polarimetry instruments will finally map these forces in detail, revealing how they channel gas into jets or stabilize disks against gravitational collapse. In massive nebulae like Carina, we might witness magnetic fields acting like cosmic traffic cops, directing material toward hungry protostars or shielding fragile molecules from destructive radiation. Some theories even suggest these fields could explain why some clouds form stars in frenzied bursts while others take billions of years, a mystery that's puzzled astronomers for decades. Then there are the surprises we can't yet predict. Every leap in telescope technology has unveiled phenomena that defied expectations, from the chaotic orbits of exoplanets to the intricate structures within supernova remnants. As we peer deeper into nebulae with these new tools, we'll likely discover entirely new classes of objects, perhaps stars born from dark matter interactions, or rogue planets forming independently of any star. The more we see, the more we'll realize how much we've underestimated the universe's creativity. This isn't just about satisfying curiosity. By studying nebulae across cosmic time, from primordial clouds in the early universe to modern nurseries like Orion, we're piecing together the story of how galaxies evolve. Heavy elements forged in stars and scattered by supernova don't just make planets possible, they dictate the very chemistry of future star formation. With 30-meter class telescopes, we might catch nebulae in distant galaxies enriching themselves with metals from the first stellar generations, watching as the universe grows more chemically complex over billions of years. The future of nebula exploration isn't just about sharper images, it's about context, connection, and revelation. Each new instrument acts like a time machine, showing us not only how stars are born today, but how they were born in the universe's youth. And as these telescopes push deeper into the infrared and millimeter wavelengths, they'll expose the coldest, darkest corners of nebulae, places where the next generation of stars, and perhaps life itself, is quietly taking shape. The cosmos has been weaving this story for 13 billion years. Now we're finally learning how to read it. Nebulae aren't confined to our galactic backyard. They paint the cosmos with stellar nurseries from one end of the universe to the other. Take the Andromeda Galaxy, our nearest spiral neighbor. Its swirling arms are dotted with glowing hydrogen regions like NGC 206, a nebula so massive it dwarfs Orion, birthing stars at a ferocious pace. Then there's the Tarantula Nebula in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This colossal star factory churns out stellar behemoths at such a rate that its core glows with the intensity of millions of suns. What makes these extragalactic nurseries so fascinating isn't just their scale. It's how they challenge our assumptions about star formation. In metal-poor galaxies like the Small Magellanic Cloud, where heavy elements are scarce, nebulae behave differently. Without enough dust to cool efficiently, gas collapses into stars less readily, resulting in fewer but often more massive stars. Contrast that with the Antennae galaxies, two spirals locked in a violent merger. Here, gravitational chaos compresses nebulae into hyperactive starburst regions, producing superstar clusters, tightly packed groups of stars so bright they outshine entire galaxies. These extreme environments rewrite the rules, showing how galactic collisions can turbocharge star birth. Some of the most revealing discoveries come from galaxies like Messier 82, a starburst galaxy where supernovae explode so frequently they create galactic winds, shredding nebulae even as new ones form. Telescopes have caught these winds red-handed, blowing bubbles of hot gas that stretch thousands of light-years. Yet amid this turmoil, stars still emerge, proving that even the harshest conditions can't stifle the universe's creative drive. Then there are the outliers, nebulae in elliptical galaxies, long thought to be stellar retirement homes. Recent observations reveal patches of cold gas where stars are forming quietly, defying expectations. Even in the relic galaxies, ancient holdouts from the early universe, astronomers have spotted nebulae with chemistry so primitive it's like finding a cosmic time capsule. Each of these discoveries peels back another layer, showing that star formation isn't a one-size-fits-all process. It adapts, influenced by a galaxy's history, composition, and even its neighbors. The James Webb Space Telescope has turned its infrared gaze to these distant nurseries, uncovering details once hidden. In the Cartwheel Galaxy, a ripple of star birth expands outward from a collision, while in the Triangulum Galaxy, delicate filaments of gas trace the magnetic fields guiding stellar formation. Every image, every spectrum adds another piece to the puzzle. Are the pillars and jets we know from the Milky Way common elsewhere? Do protoplanetary disks form the same way in metal-rich versus metal-poor environments? The answers are reshaping our understanding of how stars and the planets around them come to be. What emerges is a universe far more inventive than we imagined. Nebulae in distant galaxies aren't just copies of our own. They're variations on a theme, each one a unique experiment in cosmic chemistry and physics. And as we catalog these differences, we're not just mapping star formation across the cosmos. We're tracing the intricate web of factors that make our own galactic neighborhood just one possibility among countless others. The story of nebulae is ultimately the story of how diversity arises from universal laws, a reminder that even in the vastness of space, no two stellar nurseries are ever quite the same. The Butterfly Nebula unfolds its wings across the cosmos in a breathtaking display, one of the most striking examples of a star's final act. Unlike the turbulent nurseries where stars are born, this nebula is a monument to stellar demise, a celestial farewell painted across space. At its heart lies a dying sun, once much like our own, now shedding its outer layers in shimmering waves. The result, a delicate, symmetrical structure spanning over 3 light-years, with glowing gas streaming outward at speeds exceeding 600,000 miles per hour. But what sculpts such intricate beauty from chaos? The answer lies in the star's final throes, where gravity, radiation, and rotation conspire to create these ephemeral masterpieces. The butterfly's iconic shape, twin lobes of gas billowing like wings, isn't just random artistry. It's the signature of a star that refused to fade quietly. As the aging star exhausted its nuclear fuel, its core contracted into a white dwarf, while its outer layers expanded into a red giant. But instead of dispersing evenly, the dying star's intense radiation and magnetic fields channeled the ejected material into opposing jets, carving the nebula's distinctive bipolar structure. This isn't unique to the butterfly. Many planetary nebulae exhibit similar forms, though few with such symmetry. Some, like the Ring Nebula, display perfect hoops of gas, while others, like the Cat's Eye Nebula, twist into intricate spirals. Each shape is a cosmic fingerprint, revealing the star's mass, rotation, and even the presence of unseen companions. Hidden within these glowing shells are clues to the star's chemistry, a legacy written in light. The butterfly's vibrant hues come from ionized gases, oxygen glowing blue-green, nitrogen radiating red, and hydrogen painting faint halos. These elements, forged in the star's core over billions of years, are now being returned to the interstellar medium, enriching future generations of stars and planets. A single planetary nebula like this can eject half the star's mass into space, scattering carbon, nitrogen, and oxygen across the galaxy. Without these stellar recycling programs, rocky worlds like Earth and the life they might harbor would never exist. Yet the Butterfly Nebula is more than just a pretty face. Recent observations reveal turbulent structures within its wings, knots of denser gas resisting the stellar wind, and shock waves rippling through the outflows. These details hint at episodic mass loss, as if the star coughed out its material in fits and starts. Even more intriguing are the faint, concentric rings surrounding the central star, suggesting periodic outbursts long before the final collapse. Like tree rings recording a lifetime of growth, these ripples chronicle the star's final millennia with astonishing precision. The fate of the butterfly is as inevitable as it is fleeting. Over the next few thousand years, its gases will disperse, fading into the interstellar void. The white dwarf at its center will cool over trillions of years, a dim ember of what once was. But the story doesn't end there. Those scattered atoms will mingle with nebulae light years away, perhaps one day coalescing into new stars, planets, or even the building blocks of life. The butterfly's beauty is temporary, but its impact is eternal, a reminder that in the cosmos, even endings are beginnings in disguise. What makes these nebulae so diverse? Rotation, magnetic fields, binary companions all play a role. Some stars, like the one that birthed the butterfly, may have been spun up by a nearby companion, focusing their ejector into jets. Others, solitary and slow spinning, puff away their layers in more spherical fashion. And in rare cases, the presence of planets might shape the outflow, their gravity subtly sculpting the nebula's form. With telescopes like Hubble and Webb capturing these structures in unprecedented detail, we're decoding the final chapters of stellar lives, one dazzling nebula at a time. The Trifid Nebula is a cosmic kaleidoscope where the universe's creative and destructive forces collide in a dazzling display. Named for its three-lobed appearance, this celestial marvel is a rare hybrid, blending the fiery glow of an emission nebula, the ethereal blue shimmer of a reflection nebula, and the inky tendrils of a dark nebula into a single, breathtaking vista. Located about 5,000 light-years away in the constellation Sagittarius, the Trifid is a living laboratory where stars are born even as their older siblings tear apart the very clouds that birthed them. It's a place of contrasts where delicate filaments of dust intersect with raging stellar winds, painting a portrait of the universe's relentless cycle of renewal and decay. At the heart of the Trifid's brilliance lies a cluster of young, massive stars, their ultraviolet radiation ionizing the surrounding hydrogen gas and setting it ablaze in vivid reds, a hallmark of emission nebulae. But look closer, and you'll spot cooler, bluish regions where starlight bounces off dust grains like sunlight on a snowfield, creating the reflection nebula effect. Meanwhile, dark lanes of cosmic soot carve through the scene, blocking the light behind them and forming intricate patterns that resemble rivers of shadow. These dark nebulae aren't just voids, they're dense pockets of gas and dust, some already collapsing under gravity's pull to form the next generation of stars. What makes the Trifid particularly fascinating is the tension between its nurturing and destructive sides. The same massive stars that light up the nebula are also eroding it, their fierce stellar winds and radiation blasting away at the surrounding gas. In some areas, this erosion has sculpted towering pillars reminiscent of the pillars of creation. their surfaces boiling away under the onslaught while shielded pockets of gas within continue to birth new stars. Elsewhere, shockwaves from supernova or nearby stellar collisions compress the gas, triggering fresh rounds of star formation even as the nebula's outer layers dissipate into space. It's a delicate balancing act, one that shapes the nebula's structure and lifespan. The Trifid's complexity doesn't end there. Recent infrared observations reveal a hidden population of protostars embedded deep within its dark lanes, their faint heat signatures betraying their presence. Some of these infant stars are ejecting jets of material at supersonic speeds, carving out cavities in the surrounding gas and adding yet another layer of dynamism to the nebula's already chaotic landscape. These jets, often aligned with magnetic field lines, act like cosmic blowtorches, further sculpting the environment that will determine how and where future stars can form. But perhaps the most profound lesson the Trifid teaches is about time. This nebula isn't a static snapshot, it's a fleeting moment in a much longer story. The massive stars at its core will burn out quickly, their death scattering heavy elements into the interstellar medium. The dark nebulae may one day collapse into new solar systems, while the reflection nebulae fade as their dust grains disperse. In a few million years, the Trifid as we know it will be gone, its materials recycled into new nebulae, new stars, and perhaps even new planets. Studying the Trifid is like peering into a cosmic mirror, reflecting the processes that shaped our own solar system billions of years ago. The carbon in our bodies, the oxygen in our air, the silicon in our rocks, all were forged in nebulae like this one, then scattered across space by stellar winds and explosions. Every element heavier than hydrogen traces its lineage back to such stellar nurseries, making the Trifid not just a beautiful deep sky object, but a chapter in the story of our own origins. Its three-part harmony of light, shadow, and reflection is more than just eye candy. It's a testament to the universe's endless capacity for reinvention. Nebulae may look serene in photographs, but zoom in closer and you'll find a storm of chaos. Turbulence courses through these stellar nurseries like invisible whirlwinds, twisting and churning gas into knots dense enough for gravity to take hold. This isn't the gentle ripple of a pond. It's a full-throated cosmic tempest with supersonic shockwaves racing through the clouds at hundreds of kilometers per second. These turbulent motions are the universe's way of stirring the pot, creating pockets of high density where stars can ignite, while simultaneously flinging material outward in a balancing act that shapes entire generations of stellar birth. Supercomputer simulations have peeled back the curtain on this chaos, revealing how randomness sculpts star formation. Picture a nebula not as a static cloud, but as a dynamic fluid with eddies and currents that mimic Earth's ocean, only scaled up to light years in size. Turbulence here isn't just background noise, it's a fundamental architect. When gas collides in these turbulent flows, it creates transient high-pressure regions, like cosmic potholes where gravity gains the upper hand. Some of these knots collapse into protostars, while others are torn apart before they can coalesce, their material recycled back into the nebula's churning tides. This push and pull explains why some regions of a nebula burst with star formation while others remain eerily quiet. But turbulence does more than just stir the gas, it regulates the entire star-making economy. In calm nebulae, gravity would have free rein, causing gas to collapse into a handful of massive stars. Turbulence, however, fractures the gas into a spectrum of clumps, producing everything from tiny red dwarfs to blazing blue giants. This might explain why we see such a diverse population of stars in clusters like the Orion Nebula, where turbulence ensures no single stellar bully hogs all the material. Some theories even suggest that without turbulence, star formation would be far more explosive, with nebulae exhausting their gas reserves in frantic bursts rather than the measured pace we observe. The origins of this turbulence are as varied as its effects. Some is inherited from the galaxy itself, as nebulae form in the spiral arms where galactic rotation and supernova shocks inject energy into the gas. Other turbulence is homegrown, stirred up by the very stars the nebula births, their radiation pressure and stellar winds acting like mixers in a cosmic blender. Even magnetic fields play a role, channeling turbulent flows into organized filaments that resemble the branching veins of a leaf. The result is a feedback loop where stars shape the turbulence that then shapes the next generation of stars. What's fascinating is how this chaos leaves fingerprints on the stars themselves. In highly turbulent nebulae, protostars often end up with misaligned disks or erratic orbits, their infancy marked by the buffeting of violent gas flows. Some may be flung from their birth clusters entirely, becoming rogue stars drifting through the galaxy. Others, born in quieter eddies, mature with orderly planetary systems. This randomness isn't just a quirk, it's a defining feature of stellar demographics, ensuring no two stars or their planets form under quite the same conditions. As telescopes like ALMA map the subtle motions of gas within nebulae and simulations grow ever more precise, we're uncovering turbulence's hidden rules. It's not pure chaos, but a complex language of density waves, shock fronts, and cascading energy, one that the universe has been speaking for billions of years. And in its whispers, we're finding clues to why some nebulae blaze with youthful stars while others simmer slowly, their stellar potential locked in a dance between chaos and gravity. The more we learn, the clearer it becomes. Turbulence isn't just a side effect of star formation. It's the invisible hand that guides it. The Helix Nebula stares back at us like a cosmic eye, its eerie glow a testament to the quiet fury of stellar death. Just 650 light-years away, practically next door in galactic terms, this expanding shell of gas offers a crystal ball into our own sun's fate 5 billion years from now. What we're witnessing isn't the explosive demise of a massive star, but something far more relatable. A modest, sun-like star shedding its layers in a slow, radiant exhale. The helix's intricate structure, spanning nearly 3 light-years, isn't just a pretty celestial portrait, it's a forensic snapshot of a star's final metamorphosis, encoded with clues about how solar systems like ours meet their end. At its heart lies a white dwarf, the exposed core of the deceased star, blazing at over 100,000 degrees Celsius. This stellar ember floods the surrounding gases with ultraviolet radiation, causing them to fluoresce in vivid blues and greens, oxygen atoms glowing like neon signs, while hydrogen paints the outer rings in deep reds. But the real magic lies in the nebula's texture. Unlike the smooth bubbles of younger planetary nebulae, the helix is a labyrinth of radial streaks and comet-shaped knots, each one a dense globule of gas and dust resisting the central star's intense radiation. These structures, dubbed cometary knots, are cosmic icebergs, their heads shielding trailing tails of evaporating material, some stretching twice the length of our solar system. What's astonishing is what these knots contain. Spectroscopic studies reveal they're rich in complex carbon molecules, along with silicate dust grains that once orbited the star as part of planets, asteroids, or comets. The helix is essentially a cosmic recycling plant, where the remnants of a stellar system are being broken down and scattered into interstellar space. Imagine the fate of Earth in such a scenario, not vaporized instantly, but gradually stripped layer by layer, its atoms joining this glowing stellar shroud. Yet the helix's greatest surprise might be its symmetry. While many planetary nebulae exhibit chaotic shapes, the helix's near-perfect circular form suggests its progenitor star was a slow rotator with no disruptive binary companion. This makes it an especially clean laboratory for studying the death throes of solitary, sun-like stars. Recent Hubble observations reveal faint concentric rings within the nebula, like ripples in a pond, evidence of periodic outbursts that occurred as the star pulsed away its outer layers in fits and starts over thousands of years. But the story doesn't end with the nebula's expansion. The white dwarf at its center is still hot enough to irradiate the surrounding gas, but as it cools over billions of years, the helix will gradually fade from view. Its gases will disperse, mixing with the interstellar medium, while the carbon, oxygen, and nitrogen forged in the star's lifetime become raw materials for future stars and planets. In this way, the helix isn't just a tombstone, it's a bridge between stellar generations, a reminder that even in death, stars sow the seeds for new beginnings. What can this cosmic eyeball teach us about our own solar system's destiny? The helix suggests that sun-like stars bow out with understated grandeur, transforming their surroundings without the pyrotechnics of a supernova. And as telescopes like James Webb probe its molecular fingerprints in infrared, we may uncover even deeper truths about how planetary systems dissolve, how complex chemistry survives stellar death, and how the universe ensures no atom's journey ever truly ends. The helix's gaze holds more than beauty. It reflects our own cosmic ancestry and the quiet fate that awaits the star we call home. The Tarantula Nebula sprawls across the large Magellanic Cloud like a cosmic spider, its glowing filaments stretching over 1,000 light-years, a stellar factory operating at full throttle. This isn't just another nebula, it's the most ferocious star-forming region in our galactic backyard, churning out massive stars at a rate that dwarfs anything in the Milky Way. At its core lies R136, a dense cluster where stars pack so tightly they could fit within our solar system, their combined radiation ionizing the surrounding gas into a blistering blue haze. The energy here is so intense that if the tarantula were as close as the Orion Nebula, its glow would cast shadows on Earth. What fuels this frenzy? The answer lies in the nebula's unique environment. Unlike Milky Way nurseries, which are diluted by the galaxy's vast size, the tarantula exists in the compact confines of a dwarf galaxy. Here, gas clouds are denser, collisions more frequent, and gravitational nudges from neighboring star clusters can trigger cascades of star birth. The result is a pressure cooker scenario where gas collapses into stars at breakneck speed, especially massive ones. In just one corner of the tarantula, astronomers have spotted over 40 stars with masses exceeding 50 times that of our Sun. Stellar behemoths that burn bright and die young, seeding the nebula with heavy elements. But the tarantula's true standout feature is its sheer violence. Massive stars here don't just form, they dominate, their ultraviolet radiation carving cavernous bubbles in the gas, while supernova shockwaves rip through the nebula like cosmic tsunamis. One such bubble, spanning 250 light-years, surrounds the cluster NGC 2060, where a supernova detonated just a few thousand years ago. These explosions don't just destroy, they compress surrounding gas, triggering new waves of star formation in a self-perpetuating cycle. It's a far cry from the relatively orderly process in Orion, where stars form in relative isolation. The tarantula also offers a glimpse into the early universe, when dwarf galaxies were the dominant stellar nurseries. Its metal content, about half that of the Milky Way, mimics the chemical makeup of galaxies in the cosmos' first few billion years. This makes it a living laboratory for studying how stars formed before the universe became enriched with heavy elements. Surprisingly, the lower metal content doesn't stifle star birth. It may actually encourage it as gas cools less efficiently, leading to larger, hotter clumps. Recent observations from the James Webb Space Telescope have peeled back another layer of mystery. Infrared images reveal intricate networks of dust filaments, invisible to optical telescopes, where protostars are forming in the nebula's shadowy recesses. Some of these infant stars are already launching jets, their outflows colliding with the surrounding gas and creating shockwaves that glow in eerie greens and reds. Even more intriguing are the pockets of complex organic molecules detected in the cooler regions, hints that the tarantula might be brewing the ingredients for planets, or even life, amid its chaos. The tarantula's extreme nature raises a tantalizing question. Could such environments foster habitable worlds? With its relentless radiation and frequent supernova, the odds seem slim. Yet some theories suggest that planets forming in the outer reaches of massive star clusters might survive long enough to develop life protected by distance, or perhaps by the very disks of dust that birthed them. It's a reminder that even in the universe's most hostile corners, the potential for complexity endures. As telescopes grow more powerful, the tarantula continues to defy expectations. From its superstar clusters to its chemical oddities, this nebula is rewriting the rules of star formation. And with every new discovery, we're not just learning about a distant cloud of gas, we're uncovering the universal processes that shaped galaxies, stars, and even the atoms that make up our bodies. The tarantula's story is one of violence, beauty, and endless reinvention, a cosmic masterpiece painted in starlight and shock waves. The Veil Nebula stretches across the cosmos like a ghostly tapestry, its delicate filaments glowing in ethereal hues of red, blue, and violet, each thread a scar from a cataclysm that lit up the sky over 10,000 years ago. This sprawling wreckage, located about 2,400 light-years away in Cygnus, is all that remains of a star 20 times more massive than our Sun. When it exploded, the blast hurled material outward at millions of kilometers per hour, shredding the star's outer layers into a web of ionized gas that still shimmers today. What makes the Veil so mesmerizing isn't just its beauty, it's the precision with which it preserves the physics of destruction. Zoom in on any filament, and you'll witness the aftermath of unimaginable violence. The nebula's vivid colors aren't random, they're chemical fingerprints. Oxygen atoms, heated to millions of degrees, glow blue-green under Hubble's gaze, while hydrogen paints the scene in deep crimson. Sulfur adds golden accents, tracing shock waves where the supernova's blast front collided with interstellar gas. These elements weren't just bystanders, they were forged in the star's core during its life and scattered in its death, seeding the galaxy with the raw materials for planets and life. But the Veil isn't just a graveyard, it's a cosmic catalyst. As the remnant expands, its shockwaves plow through nearby gas clouds, compressing them until gravity takes over and new stars ignite. This process, observed in regions like the Witch's Broom, one of the Veil's most active sections, shows how destruction begets creation. The same explosion that tore a star apart might now be nurturing stellar infants light years away, a reminder that the universe thrives on cycles of renewal. What's astonishing is how much the Veil reveals about the supernova itself. The nebula's structure, a series of rippling, bubble-like shells, suggests the explosion wasn't symmetrical. Instead, the dying star likely convulsed in uneven bursts, ejecting material in chaotic jets. Some filaments are stretched into braided tendrils by magnetic fields, while others flare where the shockwave encountered denser interstellar gas. By mapping these features, astronomers can reconstruct the explosion's final moments with forensic detail, like piecing together a cosmic crime scene. Yet the Veil's story isn't static. Recent observations reveal filaments that are still moving, their shapes subtly shifting over decades. In some areas, gas is cooling and recombining, forming delicate molecular knots that might one day collapse into stars or planets. Elsewhere, invisible cosmic rays particles accelerated by the supernova's shock zip through space, their energy echoing the original blast. This dynamism makes the veil a living laboratory where the aftermath of stellar death continues to evolve. For all its fury, the veil also whispers secrets about our own origins. The oxygen we breathe, the iron in our blood, these elements were likely forged in stars like the one that birthed this nebula. As its remnants disperse, they'll blend with the interstellar medium, enriching future nebulae with the chemistry for life. The veil isn't just a relic of the past, it's a bridge to the universe's next chapter, written in gas, light, and the enduring legacy of stars that dared to die brilliantly. The Rho-Ophiuchi cloud complex drifts through the cosmos like a cosmic watercolor, its dark tendrils of dust weaving between glowing pockets of gas, a stellar nursery so close we could almost reach out and touch it. At just 460 light-years away, this sprawling region is our backyard laboratory for studying star birth, offering a front-row seat to processes that usually unfold in the distant depths of space. Unlike the grand, fiery spectacle of Orion or the Tarantula Nebula, Rho-Ophiuchi is quieter, more intimate, its stars still wrapped in the dusty blankets of their infancy. Yet within these folds, the universe is hard at work, crafting new suns and perhaps even the planets that will orbit them. What makes this complex so special is its sheer diversity. Here, dark nebulae like Barnard 44 swallow starlight whole, their dense cores shielding protostars from prying eyes. Nearby, emission nebulae glow in soft pinks and blues, energized by the radiation of young, hot stars. And threading through it all are reflection nebulae, where starlight bounces off dust grains, painting the scene in ethereal cobalt. This interplay of light and shadow isn't just beautiful, it's a physical record of the complex forces at work. The dark lanes are where gravity is winning, pulling gas into dense knots that will one day ignite. The glowing regions, those are the victory laps of stars that have already emerged, their radiation sculpting the very cloud that birthed them. At the heart of the complex lies Rho-Ophiuchi itself, a multiple star system so young it's still surrounded by the remnants of its natal disk. Observations from telescopes like ALMA have revealed intricate spiral structures within these disks, hints of gravitational instabilities that could lead to planet formation. Even more tantalizing are the chemical fingerprints detected in the surrounding gas, water ice, carbon monoxide, and complex organics like methanol. These molecules aren't just curiosities, they're the raw ingredients for future planetary systems, and Rho-Ophiuchi's proximity lets us study them with unparalleled clarity. But the real treasure lies in the shadows. Infrared and radio observations have uncovered dozens of protostars still hidden in their dusty cocoons, some so young they're barely more than warm knots of gas. One standout is the object known as ERAS 16293, a protostar erupting with intermittent jets, evidence of the violent mood swings common in stellar infancy. By tracking these outbursts, astronomers are piecing together how young stars regulate their growth, swallowing gas in fits and starts rather than steady streams. The implications stretch far beyond this one nebula. Rho-Ophiuchi's mix of low-mass and high-mass stars makes it a microcosm of star formation across the universe. Its chemistry mirrors that of distant primordial clouds, offering clues about how the first stars might have formed. And its proximity means every new telescope, from James Webb to the upcoming extremely large telescope, will train its sights here, peeling back layers of dust to reveal secrets hidden since the birth of our own solar system. What's next for this cosmic laboratory? With each technological leap, we're catching glimpses of processes once thought invisible, magnetic fields threading through the gas, shock waves from nearby supernova compressing the clouds, even the subtle gravitational tugs of unseen planets shaping their birth disks. Rho Ophiuchi isn't just a snapshot of star birth. It's a living, evolving story, one that holds the keys to understanding how every star and every world begins its journey. And as we watch this nursery unfold, we're not just observers, we're witnesses to the same forces that shaped our own sun 4.5 billion years ago. The Flying Ghost Nebula drifts through the cosmic darkness like a phantom caught in starlight, its wispy tendrils glowing faintly against the void. Officially catalogued as Sharpless 2136, this eerie reflection nebula doesn't produce its own light. Instead, it scatters the glow of nearby stars, its dust grains acting like microscopic mirrors that paint the cloud in an ethereal blue haze. The effect is hauntingly beautiful. Delicate filaments stretch across space, their shapes shifting subtly depending on the angle of starlight, as if the nebula itself is alive. But what makes this ghostly structure truly fascinating isn't just its appearance, it's the secrets it holds about the interstellar medium's hidden architecture. Unlike the blazing emission nebulae that dominate astronomy documentaries, reflection nebulae like SH2136 are cosmic introverts. Their dust particles are finer and more evenly distributed, scattering shorter wavelengths of light to create those signature cool tones. This isn't just aesthetic trivia. The way light interacts with these dust grains reveals their composition. Studies suggest the flying ghost's dust is rich in silicates and carbon compounds, materials that will one day coalesce into future stars and planets. Even more intriguing are the nebula's shadowy gaps, where denser patches of dust block starlight entirely. These could be the birthplaces of protostars too young to have blown away their dusty shrouds, hinting at the next generation of celestial objects waiting in the wings. A flying ghost isn't alone in its spectral splendor. Across the Milky Way, other overlooked nebulae weave similar ghostly tales. Take the Witchhead Nebula IC2118, a reflection nebula in Orion that seems to recoil from the brilliant star Rigel, its dust sculpted into a profile so eerily human-like it's hard to unsee. Then there's the rarely photographed ghost of Cassiopeia IC63, where hydrogen gas and dust collide in a faint, glowing veil. These structures often escape attention because they lack the vibrant hues of their more famous cousins, but their subtlety is precisely what makes them invaluable. In their delicate light-scattering patterns, astronomers decode the size, shape, and chemistry of interstellar dust, keys to understanding how galaxies evolve. What's remarkable is how these nebulae challenge our assumptions. For decades, scientists assumed interstellar dust was uniformly fine, but observations of the flying ghost and its kin reveal a far messier reality. Some regions contain grains as small as smoke particles, while others harbor pebble-sized chunks, a diversity that affects everything from star formation to the birth of organic molecules. There's even evidence that magnetic fields twist these dust lanes into intricate braids, invisible to optical telescopes but detectable through polarized light. Each discovery peels back another layer, showing that what we once dismissed as simple reflections are actually complex laboratories of physics and chemistry. The hunt for more of these cosmic apparitions is accelerating. Infrared surveys like those conducted by the James Webb Space Telescope are uncovering nebulae so faint they're virtually transparent in visible light. Some, like the newly identified Spectre Nebula in Cepheus, appear only when viewed at specific wavelengths, their structures flickering in and out of visibility like illusions. Others, hidden behind thicker dust clouds, reveal themselves through radio telescopes tracing molecules like carbon monoxide. Every new ghostly nebula adds another piece to the puzzle: how dust organizes itself across the galaxy, how light navigates these interstellar labyrinths, and ultimately, how the raw materials of stars and planets are distributed. So the next time you gaze at the night sky, remember, the brightest nebulae may steal the spotlight, but it's the faint, drifting phantoms like the flying ghost that hold some of the universe's most elusive secrets. Their whispers, carried on wavelengths just beyond our natural vision, remind us that beauty in the cosmos isn't always loud. Sometimes it's a quiet glow in the dark, waiting for the right tools and the right curiosity to bring its story to light. When we gaze at the swirling colors of a nebula, we're seeing only a fraction of the story, the ordinary matter that makes up stars, gas, and dust. But lurking in the cosmic shadows, an invisible player might be subtly shaping these stellar nurseries: dark matter. This mysterious substance, which outweighs normal matter 5-to-1 in the universe, doesn't emit or absorb light, yet its gravitational influence is undeniable on galactic scales. The question now haunting astrophysicists is whether these ghostly particles could be leaving fingerprints within nebulae themselves. The idea isn't as far-fetched as it sounds. Dark matter's gravitational pull helps sculpt galaxies, and nebulae are embedded within this unseen scaffold. Some models suggest that in massive star-forming regions like the Tarantula Nebula, dark matter could be concentrating in ways that subtly alter gravitational collapse. Imagine a molecular cloud where baryonic matter, the gas and dust we can see, is being nudged by an unseen hand, its collapse accelerated or its filaments stretched in unexpected directions. These effects would be minute, perhaps shifting star formation rates by mere percentages. But in the grand calculus of cosmic evolution, even tiny biases add up. Challenges abound in hunting these phantom influences. Dark matter's weak interactions with normal matter make its presence in nebulae incredibly difficult to detect directly. Yet there are tantalizing hints. Certain nebulae exhibit gas motions that can't be fully explained by visible mass alone. Streams of material moving faster than gravity from stars and gas should allow. Other anomalies appear in the distribution of protostars, with some clusters showing puzzling asymmetries that could point to unseen mass warping the nursery's structure. The most promising leads come from extreme environments. In the heart of galaxy clusters where dark matter is densest, nebulae might reveal amplified effects. The Perseus cluster, for instance, hosts vast clouds of ionized gas that interact with the cluster's dark matter halo in ways we're only beginning to model. Future radio telescopes like the Square Kilometre Array could measure minute velocity shifts in these gases, searching for discrepancies that betray dark matter's grip. What makes this frontier so compelling is its potential to unite cosmic scales. If dark matter indeed plays a role in nebulae, it would bridge the gap between the largest structures in the universe and the intimate processes of star birth. Next-generation gravitational wave detectors might even catch distortions in spacetime caused by dense dark matter clumps near forming stars. Every unexplained wisp or unusual motion in these cosmic nurseries could be a clue, a whisper from the universe's hidden architecture waiting to be decoded. This isn't just about solving a nebula mystery. It's about rewriting the rules of how all cosmic structures, great and small, emerge from the interplay of light and shadow. And as telescopes grow more sensitive to these subtle signatures, we may find that the most beautiful nebulae are not just stellar cradles, but cosmic canvases where both seen and unseen forces paint together. Nebulae may seem timeless when we gaze at their glowing tendrils through telescopes, but these cosmic masterpieces are fleeting here for a cosmic blink before dissolving into the interstellar void. Take the Orion Nebula, a vibrant stellar nursery today. In 10 million years, its massive stars will have blown away the surrounding gas with their fierce winds, leaving behind a scattered star cluster and a fading glow. The same fate awaits the Lagoon and Trifid Nebulae, their intricate structures unraveling like sandcastles at high tide. But this isn't just destruction, it's transformation. The dispersed atoms from these nebulae will mingle with the galactic medium, eventually coalescing into new clouds where gravity will begin its work anew. Yet not all nebulae fade quietly. Some meet more violent ends. The Carina Nebula, home to the unstable hypergiant Eta Carinii, is a ticking time bomb. When its massive stars explode as supernova, their shockwaves will rip through the nebula at thousands of kilometers per second, shredding delicate filaments and triggering chaotic waves of new star formation in their wake. These explosions will forge heavy elements like gold and uranium, scattering them into space where they might one day become part of future planets or even life. It's a reminder that nebulae are both cradles and crucibles, their deaths as consequential as their births. What about the Milky Way's darker nurseries, like the Coal Sack or Barnard's Loop? These cold, dusty regions will evolve more slowly, their dense cores gradually collapsing into stars over hundreds of millions of years, but even they won't escape change. Galactic tides and spiral arm passages will stretch and compress them, altering their shapes and trajectories. Some may drift into the galaxy's central regions, where supermassive black holes and intense radiation fields could tear them apart. Others might merge with neighboring clouds, creating supernebulae capable of birthing entire star clusters in one dramatic burst. The most fascinating question isn't just how nebulae will change, it's how future civilizations might witness them. Imagine a species evolving on a planet 1 billion years from now. Their night sky would tell a different story, with familiar nebulae like Orion dissolved into darkness, replaced by new, unnamed clouds glowing in unfamiliar constellations. Advanced telescopes might reveal nebulae in distant galaxies, their light finally reaching us after eons of travel. Or perhaps they'll observe nebulae we can't even detect today, hidden behind dust clouds or glowing in wavelengths invisible to our eyes. Technology will redefine the experience too. Future astronomers might navigate nebulae in virtual reality, tracing magnetic fields in real time or watching protostars form in accelerated simulations. They could deploy swarms of microscopic probes to analyze nebula chemistry at the atomic level, uncovering processes we've only theorized. And if humanity spreads to other stars, we might witness nebulae up close, sailing through their glowing gases in shielded ships, or mining their molecular clouds for the raw materials of interstellar civilization. This cosmic churn isn't random, it's the universe's way of reinventing itself. Every dispersed nebula enriches the galaxy with heavier elements, making each generation of stars and planets more chemically complex than the last. The iron in your blood, the silicon in your phone, the oxygen in your lungs, all were forged in these stellar factories, then scattered across space to begin new cycles of creation. Nebulae remind us that the cosmos is never static. It's a grand, ever-changing tapestry where endings are just beginnings in disguise, and every fading glow heralds the dawn of something new.